Okay. So, good afternoon, everyone. You and those that are connected right now. We have three, yes. Catalina, Luis Felipe, and Pablo. Yes, right? Okay, thanks again. Thanks to the biomedical department for having us. We are here today with Professor Joseph Bujayar and Professor Bertram Maria from University of Malta. They will be here at Los Andes all this week. Yes, they are going to stay with us all this week. And this is part of Erasmus program, a mobility Erasmus program. This is the second visit in the context of this program. And they are going to deliver two lectures. The one that we have today, Professor Maria is going to talk us about some biomedical application. Professor Maria carried out his undergraduate studies at the University of Malta. He is associate professor of the Metallurgy and Materials department. And his area of interest are surface phenomena, corrosion, tribology also, I guess. And let's say, I'm not sure, you correct me, but in many cases, you study these phenomena related with biomedical issues, not only, but in many cases. And also, he's been part of several projects where I guess the goal are to develop biomedical devices, right? And this is the context of the talk today, of the lecture today. So, Professor Bertram, the floor is yours.
Thank you very much. Thank you for
yes.
This introduction. And
I don't know if you can.
yes. Yes. So first of all, I would like to thank Professor Ortiz and Professor Escobar for organizing our visit again here at the University of Los Andes. And I would also like to thank Professor Cruz for hosting us at this biomedical session here with you. So as Professor Ortiz, his introduction, I'm coming from the University of Malta. I'm an associate professor at the Department of Metallurgy and Materials Engineering. And for those who might not know where is Malta, do you know where's Malta? Yeah. Malta is a very small island. It's the smallest nation in the EU, and it is located in the middle of the Mediterranean Sea. So you'll be very welcome to visit us. There is quite a few that have already visited us recently at the university. So today I will be talking on some research that we carry at our university related to surface engineering and the development of a MEMS gripper for biomedical applications. In particular, in our department, the Metallurgy and Materials Engineering, one of our core research is in surface engineering. We apply surface engineering to a variety of things. We do surface engineering on tools for various applications, the manufacturing industry, automotive, and many times also for research in the biomedical sector. So I'm going to mention two cases where we apply surface engineering. One, to try to mitigate the damage by corrosion and wear of metallic materials which are used inside the body. And I'm also going to mention surface engineering, which we are employing to implantable electrode materials in order to enhance their performance. Towards the end, I will also show some slides on a project where a MEMS gripper and an electrothermal actuator is being developed in order to be able to manipulate microscopic objects in particular biological cells like the red blood cell. The idea is to be able to characterize the properties of these cells, and by doing so, we could see whether the cells are healthy or not, and so on and so forth. So let's start with surface engineering. Right? For tribal corrosion. So the first application that I'm going to mention is surface engineering of metallic hip implant materials. And metallic hip implants have been a great success. They have been around for many, many years. Hundreds of thousands of implants are implanted successfully every year. There were a point, I would say 15 years ago, where one of the implants which was very popular, one configuration of implant which was very popular, was a metal-on-metal implant. And the metal-on-metal implants, overall they display low material losses, but despite the low losses that they used to produce, the debris that is released inside the body and the ions were causing a lot of problems, revision surgeries, etc. And around 2012, some 10 years ago, it became clear that these combinations are more problematic statistically than other combinations, and their popularity started dropping and dropping and dropping by a lot. Having said this, especially some configurations such as the hip resurfacing implants are still very important, because especially for young patients which might require another revision later on in life, using this type of implant will save a lot of the bone stock, of course, much more than implanting the total hip arthroplasty. So the idea of surface engineering is to try and modify the surface of these alloys, typically cobalt, chrome, molybdenum alloys, stainless steels, 316 LVM, so that in the bearing surface where the surfaces slide against each other, we try to mitigate the material losses. And throughout the last years, we did quite a few different projects where we tried different configurations and different techniques to try and mitigate this phenomenon. Having said this, it is, as you're gonna be seeing, very, very challenging. So over here we have a schematic. We have the head and the cup, and of course during gait, during movement, we have the rubbing of the cup against the bearing surface. So if we look at the surface of the metal, let's say it's a cobalt chrome, it's a stainless steel. We know these materials, stainless steels, I'm sure you are all familiar with, they are very corrosion resistant. And they are corrosion resistant because they spontaneously form a protective film on their surface. And this protective film is a passive film. It's an oxide, it's nanometric inside. And as it forms, it slows down very much the corrosion rate. However, in this configuration here where we have rubbing, this passive film is being all the time damaged and removed, and then we start getting some oxide, and the oxide gets as a third body particle within the contact, and we start having an accelerated corrosion due to wear, and the oxide, which is a product of corrosion, will start causing more wear, and we start getting a lot of synergy between the corrosion phenomena and the wear phenomena inside the body. So the total losses that we see here, we can sum them as a combination of pure corrosion. Typically, there's very little, or I would say negligible, for passive metals. Pure mechanical wear, so as if there is wear without corrosion. And the corrosion due to wear and wear due to corrosion. And these two terms tend to be very big. The synergy between wear and corrosion tend to be very big compared to the other terms. And our idea is to try and mitigate these terms. So what I will be presenting here is some ways how we try to surface engineer this metal and some testing to try to determine these different components of the total material loss and see how beneficial these treatments are to mitigate such losses. So for the testing, we do have state-of-the-art tribometers at the university, but the schematic and this testing that I'm showing was a testing which we have built in-house. It's basically a reciprocating sliding tester. Over here, we put a disk of the material of interest. Against it, we get a ball of some other material. It could be the same material or some other material. Many times we also use a ceramic counterface, alumina. Over here, we can put the solution, and connected to this substrate will be the potentiostat, where we can apply different potentials to try to remove corrosion, so suppress oxidation reactions, or just leave it floating. We can measure the open circuit potential, or we apply some positive potential to encourage corrosion and give us the ability to measure how much material is being oxidized during the test. So we can do tests under cathodic protection. So under this test, we are not allowing the metal to oxidize. So we can measure the pure wear. We can have tests which are carried out under open circuit potential without applying any potential. We just record. And we can carry out tests under some potential static anodic potential, a potential where we are favoring oxidation, and at the same time we can measure the current. So during the tests, we apply a load to get some contact stress, and we apply reciprocating sliding, and during the sliding we can measure the friction and the electrochemical parameters. So this is basically a magnification of this region, and this is the resultant wear scar that forms on the disk after the test. One of the surface engineering treatments that we do to try and mitigate tribocorrosion damage, corrosion wear damage, is the application of hard coatings. Hard coatings, typically we go for ceramic coatings, which are rather immune to corrosion. And by being immune to corrosion, we suppress a lot the failure by that repeated formation and removal of the oxide film which forms on the surface. However, hard coatings have their own problems. So over here, we're seeing a bulk coating. A bulk coating can still form some oxide. Let's say we have titanium nitride, chrome nitride. We still get some oxidation at the surface, and this during reciprocating sliding will still be it will be forming and removed during the test, and that will lead to some material losses. But typically, this type of losses will be very small, okay, and not and if that will be the only mechanism operating, it will be typically a much better performance than the uncoated passive metals. So this type of formation and removal of material and the loss, we typically refer to it as the type 1 wear corrosion damage. A more troublesome corrosion wear mechanism is what we call type 2. And in this case, over here, we can have the hard coating. There might be a coating defect, or maybe during the test itself, we can get some micro cracking. The solution will go to the interface. We get corrosion underneath the coating. This undermining will get bigger and bigger. Eventually, we start get blistering of the coating, and the coating will fail. And that's a type 2 corrosion wear. It's wear due to corrosion. Okay, it's CW. It's wear due to corrosion. We're having this corrosion, which because of it, we're getting more material loss being lost over there. And sometimes we also observe another phenomena where the rubbing surfaces will be such that the counterface, let's say, will become anodic to the material. It will roughen during the test, the counterface, and when it gets rougher due to this anodic reaction with the counterface, it will result in being more mechanically aggressive on the coating because of the roughened surface. And that this type of damage, we don't encounter it so much in our test. We refer to it as type 3 corrosion wear. Over here, I'm showing some images which I took from a paper, and these are showing a cobalt chromolybdenum alloy which has been coated with a titanium niobium nitride, a few microns thick, and they have been implanted, and the material, the bearing surface was examined some 3 to 4 years, I think, after explantation. And we could see here that they did have some problems. We're seeing this cracking and delamination. So the coating was probably failing by a phenomenon called a thin ice effect. So the thin layer was not being well supported by the substrate, and during contact, the stresses were high enough that the underside of the substrate underneath the coating deflects, and the coating then cracks. And this was resulting in weakening of the interface and basically the delamination of the coating. And over here, in this case here, we're seeing quite a lot of defects, pits inside the coating, and some blisters there, which probably have occurred because of corrosion underneath the coatings, and something which is kind of similar to the type 2 corrosion wear that we have seen before in this schematic. So these are problems that can be encountered by coatings. When you have hard coatings and they are fracturing, you have other problems because now this debris is very hard. In this case, we're not seeing much of abrasion damage, but the paper reports that much more abrasion damage was happening on the counterface, on the acetabulum cup. Okay, so in the next few slides, I'm going to show you some work that we did where we use different surface engineering techniques to try and protect one biomedical grade stainless steel, which is a 316 LVM stainless steel. And we did different surface engineering treatments. We did one with deposit around 4 micrometers of chrome nitride. In another treatment here, we applied a low temperature carburizing treatment. So basically, in this case, we diffused, or carbo was diffused at very low temperature inside the material to produce what is called NS phase, an expanded austenitic phase, which is harder than the substrate material. And apart from being harder, because it happens at low temperature, the carbon is not allowed to react with the chromium inside the steel. It remains in solution. So basically, we get increased mechanical properties without deterioration of the corrosion resistance. Over here, we have a duplex treatment. So first we did the carburizing, low temperature carburizing, and then chrome nitride. The idea was to give it better load support. So the coating will be supported better by the substrate. And then over here, we have a completely different technology. Over here, we used both layers were made by coating, by magnetron sputtering, PVD, physical vapor deposition. So we had the 316 substrate. It was coated with a cobalt chrome molybdenum carbon coating. So it's a cobalt chrome molybdenum S-phase layer. And on top of that, we deposited a chrome nitride. So we're going to be mentioning kind of 4 treatments: chrome nitride by itself, low temperature carburizing by itself, a duplex carburizing followed by a PVD chrome nitride coating, and over here we have a dual layer PVD coating, cobalt chrome molybdenum coating, followed by quite a thick layer. In this case, it was around 8 microns, followed by a thinner chrome nitride layer. And okay, here we have some cross-sectional images of the stainless steel. So this is the stainless steel which has been carburized in cross-section. Here we're seeing the microstructure of the stainless steel, the grains, twin boundaries, and this part is the carburized part. So we're having around 40 micrometers of carburized layer. Over here, we can see that the hardness increases significantly towards the surface. So the substrate is around 2 gigapascals in hardness. The carburized layer, it's in the tune of 13 gigapascals. Using X-ray diffraction, we ensured that we're not forming any chromium carbides. So basically, this is the XRD for austenitic 316 LVM. After carburizing, all we're seeing is that these 2 peaks are shifting to the left, which means the lattice remains FCC, but it is expanding. So it's an S phase. Over here we have, of course, it's showing us that the carbon content increases at the surface. These are some fractured images of the coatings, of the chrome nitride coating. Here we're seeing the 4 micrometers roughly thick chrome nitride coating. It has quite a fine fibrous growth. This coating is deposited directly on the 316 LVM. Over here, we're seeing the same coating, but now it was deposited on the carburized stainless steel. So we're seeing the coatings in cross-section. They are rather dense, but still they have this characteristic fibrous type of growth. Again, we use XRD and we get the typical crystal structure that we expect for chrome nitride. We get the FM3M crystal structure. We did some characterization of the surfaces. The untreated is the softest, carburized. We're talking about 10, 12 gigapascals. The chrome nitride, duplex chrome nitride, we're talking about hardnesses in the tune of 20 something gigapascals. So of course, these layers are much harder. We did some nano scratch testing using a conical diamond with a tip radius of 10 micrometers and with a ramped load from 0 to 450 millinewtons. And over here, these are at the same magnification. We could see that the untreated, we get a lot of deformation, plastic deformation. The carburized, we're still getting deformation, but much less, of course, because it's harder. Over here, we have the chrome nitride. We could see some transverse cracks inside the scratch track and some cracks emanating from the surface. So it shows that the deformation was sufficient that now the coating is failing. And this is the scratch test on the duplex chrome nitride, and this is showing that it is much more resistant to damage because it has a good load support provided by the underlying carburized substrate. We carried out the tribocorrosion testing. We used the counterface alumina ball. We did reciprocating for 2 hours at a frequency of 2 Hertz in a Ringer's solution. And now we're going to see some, the load was selected to be 1 Newton, which will be somewhat less than the load required to cause plastic deformation of the substrate. We don't want to plastically deform the material. We want to wear tribocorrosion test the surface, okay? So the first set of tests were carried out under cathodic conditions. So under these tests, corrosion reactions are suppressed. We're seeing that in all cases for the untreated carburized chrome nitride duplex, the material losses are quite, the amount of damage is very little. So over here, we're seeing, yes, some damage, maybe some scratches, that's the untreated. For the carburized, we're still seeing the original topography from the carburizing and some minor scratches over there, abrasion. Chrome nitride, we're getting a very smooth scar with some very fine debris. Again, the duplex, we're still seeing the topography of the carburizing underneath the chrome nitride layer, so the original topography. So in terms of damage under cathodic protection, we're seeing very little damage. But in this case, we're not allowing corrosion to happen. Over here, then we have the same tests, but this time around under open circuit potential conditions. So we're monitoring the open circuit potential, and we're doing the test. And now we can see that the damage to the 316, so this is the wear scar forming on the 316 subset, is much bigger. We can see much more abrasion damage there. So the debris over here was acting to increase the wear due to the corrosion. Sure, we're seeing this repeated fluctuations here and quite a significant drop in open circuit potential, showing that the passive film, which forms on the surface, is being continuously forming and being damaged. So definitely we're getting a lot of type 1, and we're getting a lot of, which is synergy, corrosion due to wear, and we are also getting a lot of wear due to corrosion. For the carburized is a harder material. We're still getting this sharp reduction in OCP on sliding start, showing that the passive film is being damaged, but we're seeing less abrasion damage, showing that in this case, we're getting less wear due to corrosion. The chrome nitride. In this case, now we're having quite big problems. So we're seeing the OCP on sliding start, it goes down and it's quite unstable. So some corrosion was going on, and the corrosion seems to have been happening at the interface between the coating and the substrate. How could that be happening? For the test under cathodic potential, if you look closely, it's not very clear here, but there are very fine micro cracks there. So those micro cracks will act as paths for the solution to enter and meet the interface. So if corrosion reactions are suppressed, that might not produce much of a problem. But in the case under OCP, we're seeing here that despite the friction coefficient remained very low, because the ball which was sliding on this surface was not really touching the substrate. The substrate underneath is quite rough, indicating that some corrosion activity was happening there. We're seeing some lifting off, like blistering of the coating here, showing that we were getting a lot of this type 2 damage, and basically the coating was catastrophically failed. With the duplex treated system, we had also problems. This test was only run for 1,000 seconds of sliding. After 1,000 seconds, we started observing these micro cracks, and we're seeing this failure by adhesion of the coating in these regions. And when the time of test increased, we started getting much bigger failures of the coating. Okay, we did the same test, but now under an anodic potential. So we applied a potential in the anodic direction, and basically we measured the anodic current. And over here we have quite a high anodic current, which represent materials going into solution oxidation. And we're seeing here now the wear scars are much bigger. We're getting much more mechanical damage and quite a lot of oxidation. When it comes to the carburizing, we're still getting a lot of oxidation, type 1 corrosion wear, less wear due to corrosion. For the coatings, we got, in this case, very bad results. So within the wear scar, it's not just the coating failing, but we could see these features here, and those are pits within the stainless steel. So the material underneath the coating was pitting, and we were getting these large holes, depressions inside the material. So I would say this chrome nitride on this 316 wasn't very successful at all. And you can see these pitting events over here, which for the duplex, we also had problems, micro-cracking of the coating and failure, but at least the carburizing underneath prevented the substrate from undergoing pitting corrosion. But nonetheless, the results there are not satisfactory. So basically here a bit of a summary. So tests under open circuit potential, we're seeing the untreated, we get most of the losses. This black is pure mechanical wear. This is the synergy, wear, corrosion wear. Carburized, we're getting less synergy. The chrome nitride duplex, the amount of material losses is very little, but the coatings are failing in a catastrophic way, which is not satisfactory. For tests under anodic potential, of course, the material losses are much more. We're seeing that the corrosion due to wear, this cycling, removal, and formation of the passive film accounts for the biggest loss. Carburizing is more resistant for wear due to corrosion. The coatings displayed, if you had to measure the total loss by the profilometer, much less losses, but still these coatings were failing catastrophically. So basically these treatments on 316, I would say, were not very promising at all. Then we went to this other strategy where we deposited a dual layer chrome nitride coating, dual layer cobalt chromolybdenum carbon followed by chrome nitride. We did similar testing for 2 hours, and now that is the SCM image after the test. And you can see that after the test, very little losses were incurred by the chrome nitride. So this was quite promising. So over here, we're seeing that under anodic potential, the current for the chrome nitride S coating, which is 316 cobalt chromolybdenum carbon chrome nitride, remained low and at the end of the test, it went back down to 0. And over here, we can see that over here, the total losses by this coating, chrome nitride S, I haven't mentioned this, are very satisfactory. So this coating substrate combination, yes, deserves further investigation because it does at least show promise under these test conditions. So we have seen that 316, they do have poor tribocorrosion performance. They are very susceptible to localized corrosion. Low temperature carburizing, we got better tribocorrosion response. However, we were still getting quite a lot of synergistic losses, in particular type 1. Chrome nitride and duplex showed high resistance to type 1, but unfortunately, they were exhibiting catastrophic failure, mainly by the type 2 corrosion, where the multiple layered PVD coatings showed most promise towards tribocorrosion protection for longer term use. Okay, and this dual chrome nitride S coating displayed quite excellent tribocorrosion performance under that 1 Newton load. Okay, of course, this coating will require much further test and long duration test to see how it will behave when the coating starts thinning down after long-term use. We did some similar tests on another very popular alloy, the cobalt chrome molybdenum alloy, and in this case, we selected that both the disc and the counterface will be made out of a cobalt chrome molybdenum alloy. So we used a biomedical ASTM 1537 alloy for the disc, and we used stellite 21 as the counterface ball, as the counterface material. In this case, we only looked at this coating, cobalt chrome molybdenum S phase deposited via PVD, followed by chrome nitride. So over here we have a cross-section of the coating as viewed by the SCM, and we're seeing this characteristic again, fibrous growth for the top chrome nitride layer and the somewhat more dense coating for the cobalt chrome molybdenum S phase underneath. We did some characterization, XRD for the chrome nitride, the hardness, some scratch testing. We can see with scratch testing, we can hardly see any difference in the surface topography. So we're not seeing any cracking, good load support. We did tribocorrosion testing, this time under a normal load of 3 newtons. And I'm only showing here now some results under anodic conditions. Over here, we carried the tests in ringer solutions, and in ringer solutions where we had some protein, some fetal bovine serum. And as you can see, the untreated, we're getting high current, high type 1. In bovine serum, the untreated is exhibiting much less current because the protein forms a film on the surface which limits anodic corrosion. For the chrome nitride, we're exhibiting almost 0 current in both cases. Yes, because it's very resistant to tribocorrosion. Over here, we're seeing the friction coefficient. For the untreated, we're seeing quite a high friction coefficient, but for the chrome nitride, we're seeing consistently both in ringers and in ringers plus bovine, a very low coefficient of friction. For the untreated tribopair, we can see that the addition of proteins are very beneficial to lower the coefficient of friction. It's showing that this proteins form some layer which is very lubricious on the surface. We did some tests under anodic. We have the disc and the ball. The untreated, we're seeing quite significant amount of abrasion damage. This is in contrast with chrome nitride. We're seeing here some undulations on the surface, but in general, the scar is very smooth. In fetal bovine serum, the total losses were less, but still for the untreated tribopair, we were still getting a lot of abrasion. So still type 1 and corrosion due to wear and wear due to corrosion. However, the overall losses here were less, mainly because of the proteins, which despite the damage to the passive film, they still limit the amount of oxidation from the surface. Chrome nitride S, we're seeing over there that the amount of losses were minimal. This is some 2D profiles in fetal and in ringers. So this is 2D profile using profilometer across the wear scars. We're seeing chrome nitride tribopairs, very little loss. The untreated, we're getting much bigger losses. Less losses in bovine, but for the case of chrome nitride, independent of bovine or not, the losses were smaller here, but relatively much smaller than those exhibited by the method. These are the corresponding profiles on the balls, okay, which tend to replicate, okay, the topography of the disc. So over here, we're seeing quite promising results. Cobalt chrome ringers, high losses, high synergy, corrosion due to wear and wear due to corrosion. When we test in fetal bovine serum, the corrosion due to wear, the type 1 is reduced by a lot. Yes, because it's acting as a barrier to corrosion. The chrome nitride S, both in ringers and in fetal bovine serum, we're getting much less losses. So this is now quite a promising result. What we did, we extended the tests on these coatings for 24 hours now. So quite aggressive. In ringers, after 24 hours, we noticed that the top chrome nitride layer thinned so much that it started cracking and failing by this thin ice effect. The coating only fractured the top chrome nitride, not the under layer of cobalt chromolybdenum carbide. In the fetal bovine serum, after 24 hours, we could hardly see any damage. So now, the interesting question is, yes, these coatings in fetal bovine serum, which is more, is better mimicking what is inside the body. We're getting much better performance. But what will happen if we test for even longer and longer periods and the top layer will thin and thin and thin? Will it fail gradually? Will it fail catastrophically? That is something that we have to see. But these results are quite interesting. We also carried out some fib cross sections inside the scars, and we observed that any cracks which were forming here were all being limited within the chrome nitride cobalt chrome molybdenum interface. Okay, over here we're seeing some schematics of how the failure was happening. For the untreated, we were getting quite a lot of damage. For the chrome nitride S, after 2 hours, almost no damage. After 24 hours, in fetal, in bovine serum, sorry, very little damage. In case of ringers, we got thinning and fracturing of the outer chrome nitride layer. So this is quite some interesting work, and recently we have published a paper on it over there. Okay, so it took me quite more time than I of course thought, but I will now jump to another application where we have, it's another multidisciplinary project where we're applying surface engineering now for for neural interfacing electrodes. Here it's work carried out by student, a PhD student, Janelle, under my supervision and that of Professor Wismayer, who is a member from the Faculty of Medicine and Surgery at the University of Malta. And yes, the treatment, the prognosis, the management of diseases, of injuries in the neural system have benefited quite a lot in the last decades from the application of neural interfacing electrodes. And this project is about trying to get better electrodes which can last longer, which can interface better with the neural tissue, which are resistant to chemical degradation, and which can apply, which will apply higher stimulus for many cycles without experiencing much deterioration. And in this case, we were studying titanium nitride. Titanium nitride is a very interesting material. It's a ceramic. It is used in many applications. It's used a lot in tooling. It's used in the biomedical sectors as a protective coating, for example, for scalpel blades. It is also used in the semiconductor industry as a conductive ceramic to isolate metal contacts from the active, let's say, semiconductor material, and while acting as a diffusion barrier. In this case, the titanium nitride, we're using it as the main interface or as the starting material for these electrodes. And titanium nitride, when it's dense, it's not very suitable for the application because it does display quite a high impedance, and at the same time it displays a rather low charge storage capacity, and there are many competing materials which are far better than that. However, when this material is deposited using PVD to produce a very porous material with a very high surface area, by doing so, we can drastically reduce its impedance, and we can increase by a lot its charge storage capacity. Why? Because by increasing the surface area, we're increasing the electrochemical double layer at the surface, and this titanium nitride, which is over stoichiometric, which is rich in nitrogen, has also some other effects. We call it pseudo capacitance, where at this surface we can have Faradaic charge transfer, which also contribute to an increased capacitance. So TIN is a supercapacitor. It benefits from the electrode double layer, from the Helmholtz layer, and also from Faradaic reactions. Porous TIN has many beneficial properties. It is highly conductive. It is a supercapacitor, especially when we deposit it with an over stoichiometric composition with a nitrogen-rich chemistry. We have seen that it gives very high cycle stability. We use cycle voltammetry curves, and after 10,000 discharge cycles at a cycle rate of 1,000 millivolts per second, the properties remain more or less the same. So it's very attractive material choice for neural interfacing. However, it has some drawbacks. One main drawback, it is highly susceptible to fouling. So fibrous tissue can easily grow on its surface, especially when it's porous. It has a very high stiffness. We're talking about a stiffness in the tune of 170 gigapascals. This is much bigger than the stiffness of the neural tissue. So on implantation, you can get inflammation, and the neurons won't like very much that very stiff surface. It is outperformed by some emerging electrode designs because some designs have similar or slightly better electrochemical properties. But in addition to that, they have other multifaceted approaches. For example, a softer surface, a surface which is more resistant to fouling, a surface which is more conductive to neural growth. And therefore, new solution must be devised to tackle these problems, these issues. And one strategy was to roughen the substrate, in this case it's titanium 6-4, prior to the deposition of the porous TIN coating. And this roughening of the substrate prior to deposition of TIN was done for two aims. One, to try to reduce the amount of fibroblast attachment to the electrodes, and two, to improve anchorage by micromechanical retention of subsequent coatings which are deposited on this TIN. And we have the TIN deposited on smooth titanium 6-4 and three other TINs which were deposited on substrates with an increased roughness. And we have seen that after seeding the surfaces with dermal fibroblasts, increasing the roughness prior to deposition resulted in a drastic, about 50% decrease in fouling, which has been quite a positive result from that aspect. And over here, we're seeing a high magnification of this one here, and we're seeing that with this roughening, we're getting this clusters of coating with this star-shaped features with all these pits, and this was somewhat inhibiting the fibroblasts from growing and proliferating on the surface. So this dramatic increase in surface area and surface texture allowed for more experimentation, research, and one of them was now to deposit on the roughened TIN an by electro deposition, a conductive polymer coating. And we deposited a conductive polymer. We use PEDOT PSS. Okay, this is intrinsically microporous. We have seen that by depositioning this PEDOT PSS on TIN from the cyclic voltammetry curves, this is for TIN, this is for different thicknesses of PEDOT, we start getting higher charge storage capacity and also a lower impedance. So this coating helped us to further reduce the impedance of the electrode, to increase further the charge storage capacity now from 105 to 180. It increased the cycle lifetime, and now it became more comparable to electrode materials. So basically over here, we're seeing that the impedance at 0.1 Hertz after many cycles at 1000 millivolts per second, which is typical frequencies used for neural simulation, did not affect much of the performance. However, we still have problems here with fouling, because with fouling, with PEDOT, we were still getting growth of fibroblasts, which was even more than we were getting with the roughened TIN. So the next line of surface engineering was now to add an alginate, a hydrogel, okay, a natural hydrogel. And the idea to add a hydrogel was, the main idea was to suppress fibrous encapsulation, of course, at some expense of the electrochemical properties. And we deposited these sodium alginates using electrode deposition. So we used a mixture of alginate with calcium carbonate. The samples were connected to the anode of the power supply. At the anode, we're getting this electrolysis. H pluses getting more acidic. H pluses were reacting with the calcium carbonate in the solution, producing this divalent Ca2 plus, which then, when they encounter the sodium alginate, they end up gelling the alginate, forming this calcium alginate at the surface. Of course, a lot of trials were done over here, but we got quite good control on the deposition. After the deposition process, the alginate were further hardened in a solution of calcium chloride. Calcium chloride is a more potent hardening agent. However, using it from the start is problematic because you get very ununiform coatings. And with the alginate, we attained a highly anti-fouling now surface with decent electrochemical properties. So with adding of this hydrogel, it does not significantly affect the electrochemical properties. It discourages fibrous attachment, minimizes elastic mismatch, and we can also get some tunable properties for neural growth. Last time I visited here, Los Andes, we also seen some research where neurons were being 3D printed in hydrogels, and basically this interface will give the ability that we can modify further this layer, and in fact, in our case, some neuroblastoma cells were seeded and differentiated on the hydrogel surface into neurons, and you could see the cell bodies and this fibrous growth, which are characteristic of the neurons, growing on the surface, showing that yes, the hydrogel is not or encourages neural growth, but at the same time it discourages fibrous growth, which is basically what we want over here. Okay, so quite a lot of investigation has been carried so far on this topic. Of course, one can investigate further things like putting growth factors, drug release agents, etc., and tune these materials, these surfaces, according to the needs of the application, which are very diverse. Okay. Yes. Thanks. Okay, some questions. Yes. I had some more slides with the MEMS, but some questions. Yes. So I hope I explained slowly enough that you could follow. Yeah. So we've been working with the corrosion for much longer than with this system, but at our department we always look forward when we have the ingredients of surface engineering, biomaterials, and interdisciplinary. This makes the projects very interesting. And, yeah.
Maybe I have one question in this sense, and
yes.
How are the relation between medicine faculty staff and material science staff? I mean, because I guess that in biomedical there here, the kind of project you carry out, you deal with this kind of communication interdisciplinary.
Yes. Yes, this work has been possible because of this good relationship between us and the faculty of medicine. However, this always boils down to personalities. So in my case, in the case of Professor Buhajar, we tend to work with one person, especially from the medicine side, who is very enthusiastic, very willful in order to get into this multidisciplinary aspects, and so we get a lot of support in that regard, and that is important. But yeah, you find persons both from every sector where they will find it more difficult to go outside their bubble. But on the other hand, then you find people who get very excited in exploring, these research problems where, and in a way, yeah, we are quite lucky. We've been quite lucky on a number of projects that we got, quite a good support in that regard.
You are part of the same university.
We are part of the same university, yes.
You work Santa Fe, right? And how does it work? Because there is just one.
There are cases, there are success,
Yes.
but it's difficult to get a doctor to involved, to get
Involved in the
involved
project,
because
yeah.
what happens a lot here is that they want to get paid for even very early stages of the research. So it's really difficult to get involved in projects. However, there's some
Yeah.
doctors that they get very excited for
Yes.
the possibilities of the research, and they work for years.
Yeah. Actually, Professor Bhajar can explain as well. On some projects, we get also involved surgeons from the hospital, which is adjacent to our university. And yes, search.
It's difficult to be fair because doctors here in Malta have very long hours. So very long shifts, like 80 hours per week. Shifts. So it doesn't match really well with research, especially with cells, because with cells you need to be there. You cannot go there for a week and then forget them for a month because they die. So it's not like material science. But we had some success, but also some difficulties. Fortunately, there are two consultant orthopedic surgeons who are interested in research. So they have joined us on a number of projects. Tomorrow I will give a talk about one of them, and they are heavily involved. But we also had orthopedic surgeons perform operations on tail-and-back cadavers as well. So they gave us a good 2 hours to do a hip joint replacement on a human being, but a cadaver. And that was very good because you learn a lot from them because they have the expertise. But
And they can give you direct feedback
because they are
of the
the end user,
application.
it's not the patient. In biomaterials, the end user is the surgeon and the patient. The patient is the end user, but has no say on what he receives or not, or how the operation will be done and what are the requirements. So the surgeon is very important in our
I have one question related with the tribology studies, with the connection of the interaction with the long-term properties, for example, fatigue or the fracture elements. What the relation with the result is not necessarily.
Yeah, in this, Mela, for this particular application, where you have the bearing and the aspect of fatigue, I would say, is rather limited because the actual stresses involved at the surface are quite low. And especially from the aspect of the materials, they are very clean materials. So the aspect of having cracks nucleating inside the bulk, and then I would say I won't foresee fatigue at the surface will be of a major problem. So it's quite different from, let's say, from when you have bearings which are really put under very, very high stresses. Having said this, it depends, of course, on the design then of the implant, because if you have implants and you have edges or that then are subjected to higher stresses, then yeah. So in this case, for the tribological testing that we do, these contact stresses that we use are typically much higher than the reality. And they are higher in order to enable us to shorten the test, but with, of course, we limit how high they are, not to induce any plastic deformation, because then if you do so, we start changing the mechanisms of damage. However,
is exponential when you go. I had the opportunity to do hip joint simulation in Germany, and the test was approximately for 4 months. But the cost is a big pesos is 40,000 euros. 40,000
for a test,
for a test.
which is enormous.
It's a
So
huge budget for us. It's unless you have a project and you have defined the money for that.
definitely, it won't be the test to shortlist the materials for sure.
To give you an idea.
It won't be a test to shortlist the material.
So 40,000.
Hey, thanks.
4,200. It's 168 million, no? Or no?
Yeah, probably yes.
Yeah, 160 million.
Yeah. Yeah. Yes. To test in the yeah. But I don't think, especially with the metals, because then of course with ceramics and things that's but with the metals, I don't think in this area fatigue will be of a major. But yeah, the problem with coatings, as you see, you try to solve a problem, but then you start creating others. So, and when you go for new designs and in complex environments like this, that you have corrosion and wear and so many factors, you have to really do testing to foresee problems that might arise in application.
And these coatings are for like new, I don't know, these things that we are going to put in the brain. These research is for making new ones, or it's like for taking patients that already have this
Implant?
these implants and they have maybe problems because they're getting damaged, so they can be replaced.
Yeah.
Or kind of things, or
No,
making new ones?
yeah, I think the idea here is to have new ones, which, for example, can be used for, let's say, chronic applications, where they can give you better performance for longer term use. But again, it's more of a projects where you're conducting research, you're exploring new ideas, and then, as you know, the research will lead you in the yeah. Yeah, to application. Yeah, definitely. For example, in this case, we're depositing these layers on materials which are few millimeters in diameter. But again, if you want to go to, for example, multiple electrodes with the same concepts, then you have to scale those ideas to a smaller scale, etc. So, but you have to start, of course, with something. But yeah, so basically, this work has been largely the work of one of our PhD students. The starting was we were having coatings from these coatings we brought them from a Danish technology institute, and they already had some experience with the application. The idea was to further modify the substrate before deposition and the subsequent treatments to enhance and surpass the limitations that we have. But of course, yeah, much more work has to be done. And yeah, for us, having the main researcher is an engineering student with a good background in biomedical engineering. But having the student, doing the electrochemical investigation, the characterization, and then working within the biology lab, it's quite a task. You need a multidisciplinary, yes. And as you said, because we have the support that the student can be trained in the different labs, because else it will be much more difficult. Okay. Thank you. Marcel. Yeah. I was going to show, but actually, I would have had a problem because I had some animations. That's another project that I was going to show you, was this MEMS, Microelectomechanical Systems. And we were investigating different actuation mechanisms. The idea to get these grippers, which can manipulate very accurately micro objects, such as cells. And basically, yeah, we devised some designs here, electrothermal actuators. So these are, here we're talking about 1 millimeter by 1 millimeter. So these are designed, and then we print them at Europractice. So it falls under MEMS cap. Basically, you send them the design, and they can print the design for a few €1,000. But this is mainly for research, because if it wasn't, it will cost much more. So basically, you can apply a potential. The current flows through this, they expand, and you get this micro movement. So we get this arm, for example, and it starts moving like this. And if you have something which is symmetrical to it, you can have a gripper. All right, you can have a gripper. And the idea with these grippers, we investigated quite a few designs there. The idea of the gripper is to characterize, for example, cells or microspheres, which are used for tissue stiffening. There are some conditions, for example, malaria. Malaria will stiffen the outer part of the red blood cell in a way that it can be measured. So by having this technology, you can grip a cell, deform it, study the deformation characteristics of the cell, and from there you would know whether it is a healthy or a sick cell. So this is another interesting project where we as a department we are part of it, but we collaborate a lot here with the IT, with the microelectronics and electronics department at the university. So here again, it's engineering and the IT, developing a device, but mainly one potential application is for a biomedical application. So this was it's quite, you get so you buy wafers, you get a wafer, you get a silicon substrate which is insulative. You get a silicon on insulator. This is an oxide barrier coating. This soil layer is silicon, but it is doped, so it is electrically conductive. You can put metal pads, and then you can pattern this part into different mechanical structures, as you've seen. You can edge the substrate, okay, to allow movement of the. So it's incredibly versatile. The technology, the patterning, it's very versatile. And then we have a student who is working on this, and one of his main strengths, apart from designing these, is in the numerical simulation, FEA. And he developed quite a few models to tackle, to simulate them in a multi-physical physics approach, taking into consideration the electric part, the thermal part, and then feeding the results into a structural module. And then he went for other modules where he takes into consideration the fluid, which could be air, which could be blood, which could be whatever. Yeah. Basically, Pablo, we'll learn a lot we learn all the time from these projects. Did you really?
Thank you.
Yep.